In previous classes, we have already discussed some mechanical properties, mainly applicable for our engineering application. That mechanical properties we have already discussed. And after that, whatever we have done, the test, some hardness test, that hardness test, several different tests are there, mainly Brinell hardness test, Rocker's test, and Vickers test. All those tests we have already completed in our previous lessons. Now, in our today's class, we will discuss mainly the tensile test method and what about the mechanical property obtained from our tensile test and stress strain diagram. Now all of you know that is already known to you people that what is engineering stress mainly. If you say that stress means nothing but the our force per unit area, or we can simply say the average uniaxial tensile force by cross sectional area. That gives you the engineering stress. It is known to you, all of you, and we have already discussed also in prior class. Now strain is nothing but that the change in length of the sample divided by our original length. That gives you the strain. Now what tensile test? We have to provide, or we will keep the sample for the tensile test measurement, and then we have to give some ultimate tension load, and we will look about the whatever the change of the sample is happening throughout the process. That is mainly the tensile test method, or we will get different mechanical properties step by step from this method. Okay, now if we go the next slide mainly, that is the tensile test. What it is mainly? External force is applied for unit area on a material. Material means whatever the object or whatever the given sample we want to go for the testing at the tensile test. That is the material, and it results in the stretching of the said material. How much tension they can resist. After that, the final point gives you the fracture mainly. Up to that fracture, whatever this some point we will get, that we are saying the tensile test, and I will come the later mainly. That is the tensile test leads to the elongation of any material due to the external stretching force. Elongation means we are providing the tension or load, then the material is elongated. Okay, but up to how much time? That only we are measuring from this test. Tensile strength needs already I have already discussed mainly. Okay, now first I have already presented here the stress strain diagram. Stress, what it is stress, and what is strain we have already discussed. Now how the tensile test and stress strain diagram are very important for any mechanical properties for any object or material or given sample value. Okay, if we divide the region, the initial to final region of the metal object through this stress strain diagram, simply we can divide the region in two regions, that is called the elastic region and plastic region. Clear? The what is elastic region? The whatever of this I have already seen, I will discuss later on. Here I am saying it's O, A point, B point, C point, D point, and E point. Those are the different points. I have already made it. I have taken from the literature this graph. Now this point, please check that up to this one from 0 to B, this region we are saying comes under the elastic region, and beyond this region it's nothing but the plastic region, and again we can divide this plastic region in two sub region, that is the strain hardening and necking. Now all of you know, if we are saying it's an elastic region, why we are saying so? Okay, we are saying that if we check that first the 0 to A, this region, how the material will behave if we apply the tension or any load. What will happen? Up to this region it's a comes under nothing but proportional limit. Proportional limit means if we provide the tension on load and if we release the load, what will happen? The material will again gain its original property. Okay, that's why we are saying elastic region means it is the elongated one, but if we leave the stress, then again it will come back to its original state. Here you see the OA line represents the proportional limit. What I have just now said, where the material body obeys the Hooke's law. Okay, and this line can help students to calculate the Young modulus. All of you know that one, Hooke's law and Young modulus. Okay, this region we are saying it's a, just I am coming back here. You can check from this region. You see why we are saying it's a elastic region. The material deforms in response to applied stress. We have already given the stress or load, meaning it returns to its original shape once the stress is removed. Clear? The relationship between stress and stress is linear here. That's why we are saying it's a proportional limit. This point. By Hooke's law, what is Hooke's law? It states that the stress is proportional to strain. What should be the applied stress? In that way, the elongation will be there and the strain. The stress proportional to the strain. That is the OA region, and we are saying it's a elastic region. After that region, we are saying that is the yield point. Why we are saying yield point? You see which point. You can check that one. A to B. A to B and B to C. What is this A to B? Well, you see here, this B point we are saying it's a upper yield stress point, and C point we are saying it's a lower yield stress point. Yield point mainly. Yield point. What is yield point here mainly? You see, yield point. Beyond a certain stress, if we increase the stress beyond the proportional limit, what will happen? The material begins to deform plastically. Means now it's entered the plastic region, or we can say it's a transition region from elastic region to plastic region. That is the transition state or transition region. It undergoes permanent deformation. Means if we leave the stress or taken out the stress, then what will happen? It can't be regain the original shape. The yield point marks the transition from elastic to plastic deformation. I have already shown you initially in that graph or when you drawing that. First one is the elastic region, then that is the plastic region. Clear? Next point, in plastic region, you can see this is the mainly, this we are saying this is the mainly plastic region. Clear? Okay. I think all of you got that one. That is the plastic region mainly. Here. In this region, the materials continues to deform plastically with increasing stress. We are gradually increasing the stress and the plastic region is happening mainly. Undergoing the significant strain without a proportional increase in stress. Okay? The plastic deformation is irreversible and the material shape changes permanently. Means it's already came to the plastic region and whatever the material is plastically happen and deform permanently. We can get the original shape again. Next point is the ultimate tensile strength. Which point mainly here? You see. We can say from this graph, the D point on the graph is the point beyond which students, means all of you can observe that, complete failure of the object. Okay? This point is stated as the ultimate stress point. Which point mainly? This point. Beyond this point is the, we are saying, this is the maximum point, or we can say the material can handle up to this point. After this point, the fracture will come, and this point, that's why we are saying that it is the ultimate stress point. Okay. Here, D point on the graph is the point beyond which students can observe that the complete failure of the object as it crosses the maximum stress, and this point we are saying is the ultimate stress point. After that, whatever just now we have already shown to you, E, the final point, E, that is the fracture or breaking point. Okay, that point fracture happened. That is the last point in this region. This is the fracture happened. Okay. Okay. All of you got that one? We have already said that is the 0 to A, that is the proportional limit. After that, that is the total. Both are having the total 0, sorry, not 0, it is O only. O to A, B, C point. That is the elastic point. And the first is B point, the upper yield point. C is the lower yield point. And after this C point, that is the plastic region, and the D point gives you the ultimate stress point, and that is the final point we can say. If we beyond go that point, the stress, then fracture will happen. Fracture will happen. Okay, that is the fracture point. Beyond the ultimate stress and strain, the material experiences a rapid decrease in stress leading to the fracture or failure. Okay. This fracture point marks the end of the stress strain curve, indicating the material's ultimate failure under tension. Means on that stress, that material will fail. Okay, and completely fracture. Now, another two, fracture toughness and flexural strength. Those are the characteristics from where the fracture toughness. What it is, only fracture toughness is a property that describes the ability of a material with a pre-existing flaw or crack. All of you know that one. To resist the fracture, that is called the fracture toughness. Okay. Here, one simple small formula is there. That is the critical value of the stress strain increasing factor, that is called the fracture toughness, represented by the KIC, okay, of the material in terms of the fracture stress sigma f and the crack length of for an edge crack or 1/2 of the internal crack length. That is the KIC is equal to capital Y into sigma f root of pi into A. Okay. Here, the fracture toughness represented by the KIC, and the value in SI unit is the megapascal into A root A. Okay, that is the fracture toughness. Another one property is we can say it's a flexural strength. Flexural strength. What it is? This is known as the modulus of rupture. Okay, it is the stress at which a material breaks or fracture under a bending load. Okay, under a bending load, what should be the fracture that we can able to measure that flexural strength of the material. Okay, it is an indicator of a material's ability to resist the deformation under load. That is also one characteristic property of flexural strength, mainly characteristic property of our object or material, mainly that is the flexural strength. What is the one formula is there for getting the flexural strength of any material, that is sigma f is equal to 3 capital F into capital L divided by 2 B D square. What is, while F is the load and L is the length of the span, B is the width, and the D is the thickness of the specimen or nothing but the material which we are testing the flexural strength and flexural toughness. Mainly we can say that from the tensile state and the stress strain diagram, another two property also we are able to find out, that is that mainly whatever the things we have already discussed now, mechanical property data, that I have already discussed, but all this information is written here mainly. That is the Young modulus, all of you know, E is equal to sigma by epsilon. Here, that is the Young modulus from the stress strain diagram and the Hooke's law. We are getting mainly here mainly yield strength, that I have already said. Now, what is the main significance of the yield strength? The yield strength is crucial for determining the load that a material can withstand without permanent deformation, important in structural application. Okay, that is the yield strength. Same, why we have to get the ultimate tensile strength point from the stress strain diagram. What is the main significance? What is this? The UTS. In abbreviation, we can say the ultimate tensile strength. The UTS indicates the maximum load carrying capacity of a material and is critical for understanding the failure limits for any material. Okay. And next point is the fracture strength or breaking strength, is the stress at which a material ultimately fails and breaks apart. That is the final point. What is the main significance? This value is important for understanding the ultimate durability and performance of a material under extreme conditions. Okay, that is the fracture strength. Next one is the ductility. All of you know what is the main property of any material, mainly mechanical property, is the ductility. What is this? The ductility measures the extent to which a material can plastically deform before fracture. Okay, it is often expressed as percentage elongation or reduction in area. Percentage elongation means the length will be increased, and same way in reversely reduction in area will be reduced. If your length is elongated for the applied stress or force, your area will be reduced. Okay. Significance, what is this mainly? High ductility indicates that a material can undergo significant deformation before failure. Okay. Important. What is the main importance? The importance for application of requiring flexibility. How flexible our material we are applying for any significant or appropriate application. Okay, before that one we have to test all those things. Here percentage elevation, all of you know, that is the LF minus L0 by L0. What is this? LF is nothing but the final length and L0 is the initial length. That LF minus L0 into 100, that gives you the percent elevation. Same way in reverse way, your area will be reduced. Okay. Reduction in area, percentage of reduction area is nothing but the A0 minus A. If your initially the area will be more, and finally after the elongation or this after complete stress application, your area will be reduced and percentage total area will be reduced. That is the A0 minus AF by A0 into 100. That means we can conclude in this lecture that how the tensile test and the stress strain diagram gives us the mechanical property of any material we are going for the test, and those are the different properties in different point wise we are able to get, and it is a very important test for this material for our engineering application. Okay, I am concluding here for this session today. We will discuss the next topic later.